the information provided by the neon person contains several inaccuracies. Firstly, it is false to say that all neon transformers have built-in ground fault circuit interrupters, known as GFCIs. While some manufacturers may include this feature, it is not a universal standard. Secondly, a dedicated GFCI circuit is not automatically mandated for neon transformers. GFCI protection is primarily intended for receptacles serving portable equipment or locations prone to moisture. Neon transformers, typically hardwired, do not fall under this requirement unless specifically stipulated by local codes or the manufacturer's instructions. Thirdly, the claim that a built-in GFCI is inherently more sensitive than a breaker GFCI is also questionable. Both devices are designed to trip at a similar ground fault current threshold, typically around 5 mA. There's no inherent reason why GFCI integrated within a transformer would be significantly more sensitive than a standard GFCI breaker. Fourthly, the suggestion to jumper the grounding conductor to the grounded conductor at the transformer is absolutely incorrect and creates a dangerous situation. This practice, known as bootlicking a ground, bypasses the intended safety function of the grounding system and can energize metallic enclosures, posing a severe shock hazard. The correct procedure for installing a neon transformer involves several key steps. Firstly, if the existing breaker is a GFCI type and the transformer does not have a built-in GFCI, replacing it with a standard non-GFCI breaker is appropriate. This eliminates nuisance tripping that might occur if two GFCI devices are in series. Secondly, while not always required, utilizing a dedicated circuit for the neon transformer is generally recommended. This ensures that the transformer has sufficient power and prevents overloading existing circuits, which could lead to overheating and potential fire hazards. Thirdly, properly ground the transformer by connecting the grounding conductor from the circuit to the designated ground terminal and the transformer enclosure. This provides a low impedance path for fault current, facilitating the operation of overcurrent protection devices like circuit breakers. Fourthly, and critically, never bond or jumper the grounding and grounded conductors at the transformer. These conductors must remain separate throughout the electrical system to maintain the integrity of the grounding path. I would advise making some changes to the existing installation to ensure safety and code compliance. If the current breaker is a GFCI, replace it with a standard breaker of the appropriate amperage. Verify that the existing circuit has sufficient capacity to handle the additional load of the neon transformer. Calculate the transformer's current draw based on its voltage and amperage rating and ensure that the total load in the circuit does not exceed 80% of the breaker's rating per the National Electrical Code (NEC). Always connect the grounding conductor to the ground terminal on the transformer and ensure all connections are tight and secure. Double-check that the grounding and grounded conductors are not inadvertently connected at the transformer or any other point in the circuit. Finally, if there is any doubt about the safety or correctness of the installation, consult with a qualified electrician who is familiar with neon sign wiring and local electrical codes. Here is a further breakdown of the technical considerations when dealing with neon transformers. We will start with grounding and bonding. The purpose of grounding and bonding in electrical systems is to provide a low impedance path for fault current to return to the source, which facilitates the rapid tripping of overcurrent protection devices such as circuit breakers or fuses. Grounding refers to connecting the non-current carrying metallic parts of an electrical system, such as enclosures, raceways, and equipment frames, to the earth. Bonding, on the other hand, involves connecting these metallic parts together to create an electrically continuous path. The NEC, specifically Article 250, outlines the requirements for grounding and bonding. The grounding electrode system typically consists of a ground rod, ground plate, or metal water pipe that is connected to the building's electrical system. The grounding electrode conductor connects the grounding electrode to the equipment grounding bus in the service panel. Equipment grounding conductors are used to connect the metallic enclosures of electrical equipment to the grounding system. These conductors can be wires, conduits, or other approved metal pathways. The NEC prohibits the practice of connecting the grounding and grounded conductors together on the load side of the service disconnect, as this can create a parallel path for neutral current, leading to elevated voltage on metallic enclosures and increasing the risk of electric shock. The grounding system should be inspected regularly to ensure that all connections are tight and corrosion-free. Damaged or deteriorated grounding components should be replaced immediately. Now we will move on to GFCI protection. Ground fault circuit interrupters are designed to protect people from electric shock by detecting ground faults, which occur when current leaks from a hot conductor to ground. A GFCI works by monitoring the current balance between the hot and neutral conductors. If there is a difference of 5 mA or more, the GFCI trips, interrupting the circuit and preventing electric shock. The NEC requires GFCI protection in various locations, including bathrooms, kitchens, garages, and outdoor areas, where there is a higher risk of contact with water or grounded surfaces. GFCI protection can be provided by GFCI circuit breakers, which replace standard circuit breakers in the panel, or by GFCI receptacles, which are installed in place of standard receptacles. When installing GFCI protection, it is important to follow the manufacturer's instructions and to test the GFCI regularly to ensure that it is functioning properly. GFCI devices should be tested monthly by pressing the test button and verifying that the device trips. If the GFCI does not trip when tested, it should be replaced immediately. Next, let's discuss circuit loading and overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. An overload occurs when a circuit is carrying more current than it is designed to handle, which can cause the conductors to overheat and potentially start a fire. A short circuit occurs when a hot conductor comes into direct contact with a neutral or ground conductor, resulting in a very high current flow. Circuit breakers and fuses are rated in amps, which indicates the amount of current that they can safely carry. When selecting overcurrent protection devices, it is important to choose the correct amp rating for the circuit. The NEC specifies the maximum allowable amp rating for different types of conductors based on their size and insulation type. The total load on a circuit should not exceed 80% of the circuit breaker's rating. This is to prevent nuisance tripping and to ensure that the circuit can handle the load without overheating. When calculating the load on a circuit, it is important to consider all of the devices that will be connected to the circuit, including lighting, appliances, and equipment. The NEC provides guidelines for calculating the load of various types of equipment. Now let's talk about dedicated circuits. A dedicated circuit is a circuit that serves only one appliance or piece of equipment. Dedicated circuits are often required for appliances that draw a large amount of current, such as refrigerators, ranges, and air conditioners. Using a dedicated circuit can help to prevent overloading existing circuits and can improve the performance of the appliance. When installing a dedicated circuit, it is important to use the correct size wire and overcurrent protection device for the appliance. The NEC provides guidelines for determining the correct wire size and overcurrent protection device for various types of appliances. It is also important to properly ground the dedicated circuit to ensure that the appliance is safely grounded. Let's explore conductor types and sizing. Electrical conductors are used to carry electrical current from the source to the load. Conductors are typically made of copper or aluminum, and they are available in a variety of sizes and insulation types. The size of a conductor is determined by its ampacity, which is the amount of current that it can safely carry. The NEC specifies the ampacity of different types of conductors based on their size, insulation type, and installation method. When selecting conductors for an electrical circuit, it is important to choose the correct size conductor for the load. Using a conductor that is too small can cause the conductor to overheat and potentially start a fire. The insulation type of a conductor is also important. The insulation protects the conductor from damage and prevents electrical current from leaking to ground. Conductors are available with a variety of insulation types, each with different temperature ratings and resistance to moisture and chemicals. Now, let's review transformers. Transformers are electrical devices that are used to step up or step down voltage. They consist of two or more coils of wire that are wound around a common core. When alternating current flows through one coil, it creates a magnetic field that induces a voltage in the other coil. The ratio of the number of turns in the two coils determines the voltage transformation ratio. Transformers are used in a variety of applications, including power distribution, electronic devices, and lighting systems. Neon transformers are specifically designed to provide the high voltage needed to energize neon tubes. When installing transformers, it is important to follow the manufacturer's instructions and to ensure that the transformer is properly grounded. Transformers should also be protected from overloads and short circuits. Here are a few more points to consider. Electrical enclosures are used to protect electrical equipment from the environment and to prevent accidental contact with live parts. Enclosures are available in a variety of sizes and materials, and they are rated for different environmental conditions. When selecting an enclosure, it is important to choose one that is appropriate for the location and the type of equipment that it will house. Enclosures should be properly grounded to ensure that they are safe to touch. Wiring methods refer to the different ways that electrical conductors can be installed. Common wiring methods include conduit, cable, and surface raceway. Each wiring method has its own advantages and disadvantages, and the choice of wiring method will depend on the application and the local electrical codes. All wiring should be installed in a neat and workmanlike manner. Electrical boxes are used to terminate and protect electrical connections. Boxes are available in a variety of shapes and sizes, and they are made of metal or plastic. When installing electrical boxes, it is important to use the correct size box for the number of conductors that will be terminated in the box. Boxes should be securely mounted and should be properly grounded. Electrical permits are required for many types of electrical work. Permits are issued by local government agencies, and they are used to ensure that electrical work is performed safely and in accordance with the electrical codes. Before starting any electrical work, it is important to check with the local authorities to determine if a permit is required. Electrical inspections are conducted by local government agencies to ensure that electrical work is performed safely and in accordance with the electrical codes. Inspections are typically required after a permit has been issued and before the electrical system is energized. When an electrical inspection is conducted, the inspector will check the wiring, grounding, and overcurrent protection to ensure that they meet the requirements of the electrical codes. Finally, working with electricity can be dangerous, and it is important to take precautions to protect yourself from electric shock. Always turn off the power before working on electrical circuits. Use insulated tools and wear rubber gloves and safety glasses. If you are not comfortable working with electricity, hire a qualified electrician. Here is more on the NEC. The National Electrical Code is a set of standards for the safe installation of electrical wiring and equipment in the United States. It is published by the National Fire Protection Association, NFPA, and is updated every 3 years. The NEC is not a law, but it is widely adopted by state and local governments as the basis for their electrical codes. The NEC covers a wide range of topics, including wiring methods, grounding, overcurrent protection, and equipment installation. It is an essential resource for electricians, contractors, and anyone who works with electricity. Understanding and complying with the NEC is crucial for ensuring the safety of electrical installations. The NEC is organized into chapters, articles, and sections. Each chapter covers a specific area of electrical work, such as wiring methods, grounding, or overcurrent protection. Articles provide more detailed requirements for specific types of installations or equipment. Sections provide specific rules and guidelines for particular situations. The NEC also includes tables and examples to help users understand and apply the code requirements. The NEC is constantly evolving to keep up with new technologies and safety concerns. The NFPA updates the NEC every 3 years to incorporate changes and improvements. It is important to stay up to date with the latest edition of the NEC to ensure that electrical installations are safe and compliant. Here are some of the key topics covered in the NEC. Wiring methods specify the types of wiring that are permitted for different applications. The NEC specifies the types of conductors, cables, and raceways that can be used for different types of installations. It also specifies the methods for installing and supporting wiring. Grounding requirements are designed to protect people from electric shock by providing a low impedance path for fault current to return to the source. The NEC specifies the methods for grounding electrical systems and equipment. It also specifies the requirements for bonding metallic enclosures and equipment. Overcurrent protection requirements are designed to protect electrical circuits from overloads and short circuits. The NEC specifies the types of overcurrent protection devices that are permitted for different applications. It also specifies the requirements for selecting and installing overcurrent protection devices. Equipment installation requirements specify the methods for installing electrical equipment such as transformers, motors, and appliances. The NEC specifies the requirements for grounding, wiring, and protecting electrical equipment. It also specifies the requirements for providing access to electrical equipment for maintenance and repair. Special occupancies are locations that have unique electrical requirements due to the nature of their use. The NEC includes special requirements for occupancies such as hospitals, schools, and hazardous locations. These requirements are designed to protect people and property from electrical hazards. Special equipment includes equipment that has unique electrical requirements due to its design or function. The NEC includes special requirements for equipment such as elevators, escalators, and electric signs. These requirements are designed to ensure that the equipment is installed and operated safely. Communication systems include telephone, data, and cable television systems. The NEC includes requirements for the wiring and grounding of communication systems. These requirements are designed to protect people and equipment from electrical hazards. Here are a few additional points on electrical safety. Lockout/tagout procedures are used to prevent accidental energization of electrical equipment during maintenance or repair. These procedures involve disconnecting the power source and applying a lock and tag to the disconnect switch. This prevents anyone from accidentally turning on the power while someone is working on the equipment. Personal protective equipment (PPE) is used to protect workers from electrical hazards. PPE includes items such as rubber gloves, safety glasses, and insulated tools. Workers should always wear the appropriate PPE when working with electricity. Safe work practices are procedures that are used to minimize the risk of electrical hazards. These practices include keeping a safe distance from energized equipment, avoiding contact with water while working with electricity, and using insulated tools. Workers should be trained in safe work practices before working with electricity. Electrical safety training is essential for anyone who works with electricity. Training should cover topics such as electrical hazards, safe work practices, and the use of PPE. Workers should receive regular refresher training to stay up to date on the latest safety procedures. Regular inspections of electrical equipment and systems are essential for identifying and correcting potential hazards. Inspections should be conducted by qualified personnel. Any identified hazards should be corrected immediately. Maintaining electrical equipment and systems in good condition is essential for preventing electrical hazards. Regular maintenance should include cleaning, lubricating, and tightening connections. Any damaged or worn equipment should be repaired or replaced. Remember, always consult with a qualified electrician for any electrical work that you are not comfortable performing yourself. Electricity can be dangerous, and it is important to take precautions to protect yourself and others from electrical hazards.